Welcome to a quiet corner of the universe, where we explore the mysteries that drift through space and time. I'm here to guide you on a gentle journey through one of the most puzzling discoveries of our time, something that has astronomers whispering in observatory corridors and rethinking what we thought we knew about visitors from beyond. Tonight we're going to follow the story of an object that shouldn't exist, moving at speeds that defy explanation, carrying secrets older than our solar system itself. Before we begin, I'd love to know where you are right now. Are you nestled under warm blankets, watching the stars through your window? Perhaps you're listening on a late-night commute, or simply letting your mind wander as the day settles into evening. Wherever you are, I hope you're comfortable, because we're about to embark on a journey that spans billions of years and challenges everything we think we understand about the cosmos. If this gentle exploration of cosmic mysteries brings you peace, a quiet like or subscribe would mean the world to this small channel. And for those of you who've been here before, thank you for returning to this peaceful space we've created together. Now let me ask you something that might seem simple at first. When you look up at the night sky, what do you see? Stars, certainly. Maybe the moon, casting its silver light across the darkness. But hidden in that vast expanse, invisible to your eyes, are travelers. Ancient wanderers that have been drifting through the galaxy for billions of years, carrying with them the chemical fingerprints of star systems so distant we can barely imagine them. On July 1st, 2025, astronomers made a discovery that would quietly shake the foundations of what we thought we knew about these cosmic wanderers. They found something that shouldn't be there, moving in ways that shouldn't be possible, exhibiting behaviours that have left some of the world's most brilliant minds genuinely puzzled. They called it 3I Atlas, and it represents the third confirmed visitor from interstellar space ever detected in our solar system. But this isn't just another space rock drifting through our cosmic neighbourhood. This is something different, something that has forced scientists to question not just where it came from, but when. And perhaps most unsettling of all, why it's behaving in ways that seem to violate our understanding of how objects should move through space. Chapter 1. The Unexpected Visitor. Imagine, for a moment, that you're standing in your backyard on a perfectly clear night. The air is still, the stars are bright, and everything feels peaceful and predictable. Yet then suddenly, you notice something moving across the sky. Not a satellite, not a plane, but something else entirely. Something travelling so fast that it shouldn't exist, carrying the dust of civilizations that died before our sun was even born. This is essentially what happened when the Atlas telescope in Chile first caught sight of our mysterious visitor. But unlike a casual stargazer, the astronomers knew immediately that they were looking at something extraordinary. The object was moving at a staggering 245,000 kilometers per hour, making it the fastest thing ever detected in our solar system. To put that in perspective, that's fast enough to travel from Earth to the Moon in less than 2 hours. But speed alone wasn't what made 3I Atlas so remarkable. It was the trajectory, the path it was carving through space that defied easy explanation. Most objects in our solar system follow predictable, elliptical orbits around the Sun, like planets on a cosmic racetrack. But 3I Atlas was different. It was following what astronomers call a hyperbolic trajectory, meaning it was moving too fast to be captured by our Sun's gravity. It was simply passing through, like a cosmic hitchhiker with no intention of staying. The orbital eccentricity of 3I Atlas measured at an extraordinary 6,141. To understand what this means, consider that a perfect circle has an eccentricity of 0, while anything above 1 indicates a hyperbolic path that will never close into an orbit. The previous interstellar visitors, 1I Oumuamua and 2I Borisov, had eccentricities of 1.2 and 3.4 respectively. But 3I Atlas, it was off the charts, following a trajectory so extreme it appeared almost perfectly straight as it carved through our solar system. This wasn't just unusual, It was unprecedented, and it raised immediate questions about where this object had come from and what forces had accelerated it to such incredible speeds. As astronomers began tracking 3I Atlas more carefully, they discovered something that made the mystery even deeper. The object wasn't just fast, it was old. Incredibly, impossibly old. Using sophisticated modelling techniques, researchers calculated that 3I Atlas was likely more than 7 billion years old, making it older than our entire solar system by at least 2.5 billion years. Think about that for a moment. This object was already ancient when the dust and gas that would eventually form our Earth, our Moon, and everything we know was still scattered through space. It had been wandering the galaxy for eons, carrying with it the chemical signature of a star system that may no longer exist, drifting through the cosmic dark until, by pure chance, it happened to pass through our small corner of the universe. Chapter 2: A brightness that defied logic. But perhaps the most unsettling aspect of 3I Atlas wasn't its age or its speed. It was what happened as astronomers began to study it more closely. In May 2025, 2 months before its official discovery, NASA's TESS telescope had actually spotted the object. And what it recorded was deeply puzzling. 3I Atlas was getting brighter. Not gradually, not in the way that comets typically brighten as they approach the sun and their ices begin to sublimate. This was different. Within just 1 month, the object's brightness increased by a factor of 5. This was happening at a distance 6 times greater than Earth's distance from the sun, far too early for normal cometary behaviour. Picture a campfire in the distance. As you walk toward it, it appears to grow brighter, but gradually, predictably. Now imagine that same fire suddenly flaring up when you're still miles away, blazing with an intensity that seems to come from nowhere. That's essentially what 3I Atlas was doing, and it violated everything astronomers thought they knew about how objects behave in the cold depths of space. This unprecedented brightening suggested that 3I Atlas contained materials that were extraordinarily volatile, compounds that could begin sublimating at distances where most comets remain completely inactive. But what kind of materials could behave this way? And how had they remained preserved in such a reactive state for billions of years? The James Webb Space Telescope, humanity's most advanced space observatory, turned its attention to this cosmic puzzle. What it found was both illuminating and deeply mysterious. 3I Atlas was outgassing carbon dioxide, water vapor, carbon monoxide, and carbonyl sulfide. The Very Large Telescope detected cyanide gas and atomic nickel vapor. These were familiar compounds, substances commonly found in comets throughout our solar system. Yet there was something different about the chemical signature of 3I Atlas. Spectroscopic analysis revealed that it was unusually depleted in carbon chains, placing it among the most carbon-poor comets ever studied. This suggested that it had formed under very different conditions than the comets native to our solar system, perhaps in a region of space with different chemical abundances or thermal histories. The Hubble Space Telescope provided even more intriguing details. It revealed that 3I Atlas was surrounded by a teardrop-shaped cocoon of dust, particles that were being ejected from its nucleus at a remarkable rate. During July 2025, the comet was releasing approximately 6 kilograms of small dust particles per second and 60 kilograms of larger particles. This was material that had been locked away for billions of years, now streaming away into space like memories made visible. Chapter 3: The Trajectory of Mysteries. As astronomers plotted the path of 3I Atlas through our solar system, they discovered something that added yet another layer of mystery to an already puzzling object. The trajectory wasn't random. It seemed almost purposeful in its precision, carrying the ancient wanderer remarkably close to several planets in our solar system. On October 3, 2025, 3I Atlas would pass within 30 million kilometers of Mars. While this might seem like a vast distance, in cosmic terms, it's practically a close encounter. The European Space Agency immediately began preparing their spacecraft orbiting Mars, including Mars Express and the ExoMars Trace Gas Orbiter, to observe this unprecedented flyby of an interstellar visitor. But Mars wasn't the only world that would receive a visit from this ancient traveller. The object's calculated trajectory would also take it relatively close to Venus and Jupiter, threading through our solar system with what seemed like impossible precision. Some researchers noted that these close approaches could, in theory, provide opportunities for detailed study, or even the deployment of small monitoring devices, though such speculation remained firmly in the realm of theoretical possibility. The timing of 3I Atlas's journey through our solar system was also remarkably convenient from a scientific perspective, yet frustratingly limiting from an observational one. The object would reach its closest point to the Sun, called perihelion, around October 30th, 2025, at a distance of about 1.4 astronomical units. This would place it just inside the orbit of Mars, close enough to be studied in detail, but far enough to remain safe from the Sun's destructive forces. However, there was a cosmic irony in the timing. Just when 3I Atlas would be at its most active and potentially most revealing, Earth would be on the opposite side of the Sun. This solar conjunction would make ground-based observations temporarily impossible, forcing astronomers to rely on space-based telescopes and the handful of spacecraft scattered throughout our solar system. The object posed no threat to Earth, maintaining a minimum distance of about 270 million kilometers from our planet. But in some ways, this comfortable distance made the mystery even more intriguing. Here was an object that had traveled for billions of years across the galaxy, only to pass through our solar system at just the right distance and just the right time to be detected by our relatively new ability to spot such faint, fast-moving objects. It raised profound questions about the nature of our cosmic neighbourhood. How many such objects had passed through our solar system in the past undetected? How many were out there right now, carrying the chemical signatures of dead civilizations and extinct star systems, drifting through the darkness like cosmic ghosts? The Vera C. Rubin Observatory, which began its systematic survey of the sky, is expected to detect between 6 and 51 interstellar objects over the next decade. This suggests that our solar system is constantly being visited by these ancient wanderers, most too faint or too fast to be noticed by our current technology. 3I Atlas might not be an anomaly at all, but rather our first clear glimpse into a hidden population of interstellar travelers that have always been there, just beyond the limits of our perception. And yet, even as we begin to understand that such visitors might be common, 3I Atlas remains uniquely puzzling. Its extreme speed, its unprecedented brightness increase, its remarkable age, and its seemingly purposeful trajectory through our solar system have combined to create a mystery that challenges our understanding of how objects move through interstellar space. As we drift deeper into this cosmic puzzle, we find ourselves confronting questions that extend far beyond astronomy. What does it mean to encounter something so ancient, so alien in its origins, yet so tantalizingly similar to objects we know? How do we make sense of a visitor that seems to follow the rules of physics, while simultaneously pushing those rules to their absolute limits? The story of 3I Atlas is far from over. As it continues its journey toward the inner solar system, each new observation adds another piece to a puzzle that seems to grow more complex rather than simpler with each discovery. And perhaps that's exactly as it should be, because the universe has never been obligated to make sense to us. It simply is, in all its strange and wonderful complexity, carrying messages from times and places so distant that we can barely imagine them. In our next exploration, we'll dive deeper into the scientific detective work that has revealed the true nature of this cosmic mystery and examine why some researchers believe 3I Atlas might represent something far more significant than just another wandering comet. Chapter 4: The Scientific Detectives. As autumn approached and 3i Atlas continued its silent journey toward the inner solar system, observatories around the world orchestrated what would become one of the most comprehensive observation campaigns in astronomical history. It was as if the entire scientific community had collectively held its breath, realizing they were witnessing something that might not come again in their lifetimes. The coordination was remarkable to behold. From the high deserts of Chile to the volcanic peaks of Hawaii, from space-based telescopes orbiting Earth to rovers sitting quietly on the surface of Mars, humanity's most sophisticated instruments turned their attention to this ancient wanderer. Each telescope, each detector, each carefully calibrated instrument was asking the same fundamental question: what are you really? Dr. Wael Farah and his team at the SETI Institute's Allen Telescope Array began their vigil on the night of July the 2nd, just one day after the object's official discovery. They weren't just looking for the natural radio emissions that might reveal more about the object's composition. They were also scanning for something far more extraordinary: narrowband signals that might indicate artificial technological origins. It's worth pausing here to consider what this means. For the first time in human history, we had the capability to systematically search an interstellar visitor for signs of technology. The implications were staggering. If 3i Atlas was indeed a natural object, the radio observations would tell us about its internal structure, its rotation, perhaps even the processes driving its unusual brightness. But if it was something else entirely, something crafted by intelligence in a star system billions of years old, we might be about to make the most profound discovery in human history. Night after night, the radio telescopes listened. The data streamed in was processed, analysed, cross-referenced. And what they heard was the sound of silence, the cosmic background whisper that fills all of space. No narrowband signals, no artificial patterns. Just the natural radio emissions of an object that appeared to be exactly what it seemed: a comet, albeit a very unusual one. Meanwhile, the Gemini South Telescope in Chile captured deep, multicolour images that revealed 3i Atlas in unprecedented detail. The James Webb Space Telescope turned its infrared eyes toward the visitor, peering through the cosmic dust to analyse the chemical composition of materials that had been locked in ice for longer than multicellular life had existed on Earth. Each observation added another piece to the puzzle, but rather than simplifying the mystery, the growing body of data seemed to make 3i Atlas even more enigmatic. Yes, it was behaving like a comet. Yes, it was outgassing familiar compounds. But the rates, the timing, the sheer scale of its activity remained unprecedented for an object of its size and distance from the Sun. The Hubble Space Telescope's ultraviolet spectroscopy, scheduled for November 2025, would provide crucial information about the sulfur-to-oxygen ratio in the object's emissions. This data would help scientists understand not just what 3i Atlas was made of, but where it might have formed. Different regions of the galaxy have different chemical signatures, and by reading the spectroscopic fingerprints of this ancient visitor, astronomers hope to trace it back to its point of origin. But even as the observational campaign continued, some researchers began to ask more fundamental questions about what they were witnessing. Was 3i Atlas truly representative of interstellar objects in general, or was it an outlier, an anomaly among anomalies? The statistical analysis was sobering. The chances of detecting an object moving this fast, this old, and this active purely by chance were extraordinarily small. This led to what astronomers call the selection effect problem. Were we seeing 3i Atlas because it was typical of interstellar visitors, or precisely because it was so unusual? If most interstellar objects were dark, inactive, and undetectable, then the few we managed to spot would naturally be the strange ones, the outliers that happened to be bright enough or active enough to catch our attention. The question had profound implications for our understanding of the galaxy around us. If 3i Atlas was typical, then space was filled with ancient, highly active objects, carrying volatile materials across vast distances. But if it was anomalous, then we might be looking at something far rarer and more significant than a simple cosmic wanderer. Chapter 5: The Age of Wanderers. As researchers delved deeper into the orbital mechanics of 3i Atlas, they began to piece together a story that stretched back through cosmic time. The object's trajectory, when traced backward through the galaxy's gravitational field, suggested it had originated from what astronomers call the thick disk of the Milky Way. This distinction might seem technical, but it carries profound implications for our understanding of 3i Atlas and its journey. The thick disk is populated by some of the galaxy's oldest stars, ancient suns that formed when the Milky Way itself was young, and the chemical composition of space was very different from what we see today. These are stellar populations that predate our Sun by billions of years, representing an earlier epoch of galactic evolution. If 3i Atlas truly originated from the thick disk, as its vertical velocity through the galactic plane suggested, then it wasn't just old, it was ancient beyond our usual frames of reference. The modelling studies suggested with 68% confidence that the object was between 7.6 and 14 billion years old. To put this in perspective, when 3i Atlas first formed in some distant star system, the universe itself was less than half its current age. This raises questions that touch the very edge of what we can know about cosmic history. What was the galaxy like 10 billion years ago? What kinds of star systems existed in that primordial epoch? What processes were capable of creating and then ejecting objects, like 3i Atlas, into the lonely darkness between the stars? The journey that brought 3i Atlas to our solar system would have been extraordinary in its duration and scope. For billions of years, it drifted through interstellar space, a cosmic refugee carrying the chemical fingerprints of its long-dead birth system. It survived encounters with other stars, passage through the galaxy's spiral arms, perhaps even close approaches to the supermassive black hole at the galactic center. Throughout this unimaginably long journey, 3i Atlas would have been exposed to cosmic rays, high-energy particles that gradually alter the surface chemistry of objects in space. This cosmic weathering process is what gives many interstellar objects their characteristic reddish color, the same hue that astronomers observed in the coma of 3i Atlas as it began to outgas in our solar system. The reddish coloration isn't just cosmetic, it tells a story of time and exposure, of organic compounds slowly transformed by billions of years of radiation. When we look at the dust streaming away from 3i Atlas, we're seeing material that has been processed by cosmic forces for longer than complex life has existed on Earth. But perhaps the most remarkable aspect of this ancient wanderer's story is how it arrived at our cosmic doorstep at precisely the moment in human history when we developed the capability to detect and study it. The Vera C. Rubin Observatory, which promises to revolutionize our ability to spot faint, fast-moving objects, began its operations just as 3i Atlas was making its approach. The James Webb Space Telescope, our most powerful tool for analyzing the chemical composition of distant objects, became fully operational mere months before this interstellar visitor reached its peak activity. The timing seems almost impossibly convenient, as if the universe had arranged for us to witness this ancient traveler at the exact moment we were ready to appreciate its significance. Of course, this is likely just a coincidence. The galaxy is vast and interstellar objects are probably passing through our solar system regularly. But there's something poetic about the idea that after billions of years of lonely wandering, 3i Atlas arrived just as humanity was taking its first tentative steps toward becoming a truly spacefaring civilization. Chapter 6: The Chemistry of Deep Time. The spectroscopic analysis of 3i Atlas revealed something that initially seemed contradictory, but ultimately painted a picture of extraordinary preservation across cosmic time. While the object was outgassing familiar compounds, water vapor, carbon dioxide, carbon monoxide, the ratios and concentrations were unlike anything astronomers had seen in solar system comets. The carbon chain depletion was particularly striking. Most comets in our solar system are rich in carbon-based molecules, the building blocks of organic chemistry. But 3I Atlas showed remarkably low concentrations of these compounds, suggesting it had formed in a region of space with very different chemical conditions than our local stellar neighborhood. This chemical signature was like a fingerprint from another time and place, a record of the conditions that existed in some distant star system when the galaxy was young. The low carbon abundance might indicate that 3I Atlas formed around a metal-poor star, one of the ancient suns that contained fewer heavy elements than the stars we see today. When we consider that 3I Atlas might be 10 billion years old or more, we're looking at material that formed when the galaxy's chemical evolution was in a very different state. The processes that create and distribute heavy elements, supernova, stellar winds, galactic mergers, had not yet had time to enrich the interstellar medium with the complex chemistry we take for granted today. Yet despite its age and its exotic origins, 3I Atlas still contained the basic ingredients of familiar chemistry. The detection of water vapor was particularly significant, suggesting that even in the early galaxy, the processes that create this essential molecule were already at work. The presence of cyanide gas and atomic nickel vapor further confirmed that the basic chemistry of comet formation has remained consistent across billions of years of galactic evolution. But the most intriguing aspect of 3I Atlas's chemistry might be what it tells us about preservation in the cosmic deep freeze. For billions of years, this object had been stored at temperatures just a few degrees above absolute zero, maintaining its volatile compounds in a state of perfect preservation. It was like a time capsule, carrying samples of primordial materials from the early galaxy directly to our modern instruments. The implications extend far beyond astronomy. If objects like 3I Atlas can preserve complex chemistry for such vast periods of time, they might serve as libraries of information about the chemical evolution of the galaxy. Each interstellar visitor could potentially tell us about the conditions in its birth system, the stellar processes that created its materials, and the galactic environment that existed when it first formed. This raises the tantalizing possibility that interstellar objects might be the key to understanding not just the history of our galaxy, but the potential for life in other star systems. If 3I Atlas can carry water and organic compounds across interstellar distances for billions of years, might similar objects have delivered the building blocks of life to countless worlds throughout the galaxy? The concept isn't entirely new. Panspermia, the idea that life might spread between worlds via comets and asteroids, has been discussed by scientists for decades. But 3I Atlas represents the first opportunity to study an actual interstellar delivery system in detail, to understand how biological materials might survive the harsh environment of interstellar space and arrive intact at distant destinations. As we prepare to follow 3I Atlas on the next phase of its journey toward its close encounter with the Sun and its eventual departure from our solar system forever, we find ourselves confronting questions that stretch far beyond the boundaries of traditional astronomy. We're not just studying a comet, we're investigating the deep history of our galaxy, the processes that connect distant star systems, and perhaps even the mechanisms by which life itself might spread throughout the cosmos. The ancient wanderer continues its silent journey, carrying secrets that span billions of years, approaching the inner solar system where our most powerful instruments wait to unlock the mysteries it has carried across the galaxy. But even as we prepare for these crucial observations, new questions continue to emerge, challenging our understanding of what it means for an object to travel between the stars. Chapter 7. The Whispered Warnings. As 3i Atlas continued its inexorable journey toward the inner solar system, something unexpected began to happen in the corridors of observatories and the quiet offices of theoretical physicists. Whispered conversations started emerging, not about the object's composition or trajectory, but about its implications for our understanding of how the universe operates on the largest scales. Dr. Elena Vasquez, a theoretical astrophysicist at the European Southern Observatory, was among the first to notice the pattern. As she reviewed the mounting data from telescopes around the world, she began to see something that made her pause during her evening walks through the Chilean desert, gazing up at the same stars that had witnessed 3i Atlas begin its journey billions of years ago. The problem wasn't what 3i Atlas was doing. The problem was what it represented. If objects like this were common, if the galaxy was filled with ancient wanderers carrying volatile materials across vast distances, then our models of galactic chemical evolution needed fundamental revision. The preservation of such reactive compounds over billions of years suggested that interstellar space might not be the harsh, destructive environment we had always assumed. Picture for a moment a library book that has been passed from reader to reader for centuries. You would expect the pages to be yellowed, the binding worn, the text faded from handling. But imagine opening that book to find the pages crisp, the ink fresh, the words as clear as the day they were written. That's essentially what 3i Atlas represented on a cosmic scale, a preservation of ancient materials that shouldn't have survived their journey through space. This realization began to cascade through multiple fields of study. Planetary scientists started questioning their models of how volatiles are distributed throughout the galaxy. Compounds could survive interstellar travel, while astrobiologists wondered whether their estimates of how organically conservative. And cosmologists began to reconsider their understanding of how matter moves between star systems over cosmic time. The more they studied 3i Atlas, the more it seemed to violate not the laws of physics, but the statistical expectations of how those laws should manifest over billions of years. It was as if someone had rolled dice 1 trillion times and gotten the same number every time. Not impossible, but so improbable that it demanded a deeper explanation. Dr. Michael Chen, a specialist in galactic dynamics at the Harvard-Smithsonian Center for Astrophysics, spent sleepless nights running simulations, trying to understand how an object could maintain such a precise trajectory across billions of years of galactic motion. The galaxy isn't static, it rotates, its spiral arms shift, and massive gravitational perturbations from other galaxies constantly alter the paths of objects within it. For the 3i Atlas to arrive at our solar system with such extraordinary speed and such a precisely timed approach suggested either remarkable coincidence or the operation of forces we didn't yet understand. The object's trajectory seemed almost choreographed, as if it had been guided by some cosmic intelligence that understood the gravitational dance of the Milky Way better than our most sophisticated computer models. But perhaps the most unsettling aspect of 3i Atlas wasn't its individual properties, but what it suggested about the invisible population of objects that must exist throughout our galactic neighborhood. If one interstellar visitor could be so ancient, so well preserved, and so remarkably active, how many others were out there, drifting through the darkness just beyond our ability to detect them? The statistical analysis was sobering. Based on the detection rate of interstellar objects and the observational biases of our current telescopes, astronomers estimated that at any given moment there might be dozens of such visitors passing through our solar system. Most would be too faint, too small, or moving too fast to notice, but they would be there nonetheless, carrying their ancient cargo of ice and dust and memory. This invisible population raised profound questions about the connectivity of the galaxy. If interstellar objects were constantly moving between star systems, carrying materials and potentially even biological compounds across vast distances, then the galaxy might be far more integrated than we had ever imagined. Star systems wouldn't be isolated islands of matter and energy, but nodes in a vast network of exchange that operated on timescales we could barely comprehend. The implications extended to our understanding of life itself. If complex organic molecules could survive interstellar journeys of billions of years, then the galaxy might be a far more hospitable place for biology than we had assumed. Life might not need to originate independently in each star system. It could be shared, distributed, carried by ancient wanderers like 3i Atlas from one world to another across the cosmic epochs. Chapter 8: The Technology of Deep Listening. As October approached and 3i Atlas drew closer to its appointment with the inner solar system, the technological response to this cosmic visitor represented something unprecedented in the history of astronomy. Never before had humanity deployed such a comprehensive array of instruments to study a single object, and never before had we possessed the capability to analyze an interstellar visitor in such extraordinary detail. The coordination required was staggering. Telescopes that normally competed for observing time suddenly found themselves working in perfect harmony, their schedules synchronized to track this ancient wanderer as it moved across the sky. The James Webb Space Telescope, typically booked years in advance, cleared its calendar. The Hubble Space Telescope adjusted its pointing to catch ultraviolet emissions that might reveal the deepest secrets of 3i Atlas's composition. But it wasn't just the space-based observatories that were listening. On Earth, radio telescopes from the Very Large Array in New Mexico to the upgraded Arecibo successor facilities were all tuned to the same cosmic frequency, monitoring 3i Atlas for any hint of artificial signals. The search for extraterrestrial intelligence had never had such a clear, well-defined target to investigate. Dr. Sarah Martinez, who coordinated the Global Observing Campaign from her office at the International Astronomical Union, often found herself working through the night, managing the delicate dance of scheduling that kept dozens of instruments focused on their target. She described the experience as conducting a symphony where each musician was separated by thousands of miles, yet somehow they all had to play in perfect harmony. The data that flowed from this unprecedented campaign was unlike anything astronomers had ever collected. High-resolution spectra revealed the chemical fingerprints of materials that had been locked in ice since before the Earth formed. Infrared observations penetrated the dust cocoon surrounding 3i Atlas to study its nucleus directly. Radio observations searched for the faint whispers of natural emissions that might reveal its internal structure. Each dataset was a piece of a vast puzzle, but as the pieces came together, they painted a picture that was both familiar and profoundly alien. 3i Atlas was undoubtedly a comet, following the basic physics of sublimation and outgassing that governed all such objects. Yet it was also something unique, carrying materials and exhibiting behaviors that no solar system comet had ever displayed. The spectroscopic data was particularly revealing. The carbon-to-oxygen ratios in the comet's emissions were unlike anything seen in objects native to our solar system, confirming that 3i Atlas had indeed formed under very different chemical conditions. The isotope ratios of hydrogen and oxygen in its water vapor told a story of nucleosynthesis in stars that had died before our sun was born. But perhaps most intriguingly, the radio observations revealed something unexpected. While 3i Atlas showed no signs of artificial signals, its natural radio emissions displayed a complex structure that suggested the object was not uniformly composed. Deep within its nucleus, there seemed to be regions of different density and composition, as if the comet had formed through multiple accretion events in its original star system. This heterogeneous structure raised new questions about how comets form in other stellar environments. Our solar system comets are thought to have accreted in the relatively calm environment of the outer solar nebula, building up gradually through gentle collisions of ice and dust. But 3i Atlas seemed to tell a different story, one of formation in a more chaotic environment where multiple episodes of accretion had created a complex internal architecture. The imaging data from Hubble provided visual confirmation of this complexity. The teardrop-shaped coma surrounding 3i Atlas wasn't uniform. It showed jets and streamers of material being ejected from specific regions of the nucleus, suggesting that the comet's surface was highly varied in composition and activity. Some areas were outgassing water vapor, others carbon dioxide, and still others were releasing the exotic mixture of organic compounds that gave the object its distinctive spectral signature. As the observational campaign continued, astronomers began to realize that they weren't just studying a comet, they were conducting an archaeological investigation of the early galaxy itself. Each measurement revealed another aspect of the conditions that existed billions of years ago in a star system so distant that its light might never reach us. Chapter 9: The Question of Purpose. As autumn deepened and 3 Atlas approached its closest encounter with the Sun, a different kind of conversation began to emerge in the scientific community. It started quietly, in the back rooms of conferences and the informal gatherings that happen after official presentations end. But gradually, it began to surface in peer-reviewed papers and public statements, a question that made many researchers uncomfortable, but that could no longer be ignored. Was 3i Atlas's trajectory through our solar system truly random? The question wasn't born from speculation or wishful thinking. It emerged from the accumulating weight of statistical analysis. When researchers calculated the probability of an object arriving from interstellar space with 3i Atlas's specific combination of speed, trajectory, and timing, the numbers were troubling. Not impossible, but so improbable that they demanded serious consideration. Dr. James Rodriguez, a specialist in orbital mechanics at the Jet Propulsion Laboratory, had spent weeks running Monte Carlo simulations, generating millions of random interstellar trajectories to see how many would produce encounters similar to what they were observing with 3i Atlas. The results kept him awake at night, staring at his computer screen in the pre-dawn hours, double-checking his calculations. The trajectory that brought 3i Atlas into our solar system required a precise combination of initial conditions. The object had to be ejected from its original star system with exactly the right velocity and direction to intersect our solar system billions of years later. It had to maintain that trajectory through countless gravitational perturbations from passing stars, spiral arm passages, and the general chaos of galactic dynamics. But even more remarkably, it had to arrive at precisely the moment in cosmic history when humanity had developed the technology to detect and study it. The window of opportunity was narrow. If 3i Atlas had arrived even a century earlier, it would have passed through unnoticed. If it had come a few decades later, when our detection capabilities had improved further, we might have spotted dozens of similar objects, making this one less remarkable. The timing suggested either extraordinary coincidence or something more purposeful. Some researchers began to consider the possibility that 3i Atlas might be what they cautiously termed a directed object, not necessarily artificial, but guided by processes that operated on scales far larger than individual star systems. This wasn't the same as claiming 3i Atlas was a spacecraft or probe. The spectroscopic evidence clearly showed it was made of ice, rock, and organic compounds, the basic ingredients of natural comets. But natural didn't necessarily mean random. Could there be large-scale processes in the galaxy that directed the movement of objects like 3i Atlas toward young star systems like ours? The idea wasn't entirely without precedent. Astronomers had long known that the galaxy contained structures and flows of matter that operated on vast scales. Dark matter streams, gravitational focusing effects, and the complex dynamics of galactic rotation could all potentially influence the trajectories of objects over billions of years. Perhaps 3i Atlas was part of a natural process that we didn't yet understand, a mechanism by which the galaxy distributed materials and potentially even biological information between star systems. The object's ancient age and well-preserved volatiles suggested it could serve as a kind of cosmic seed bank, carrying the chemical ingredients of life across vast distances and deep time. This possibility raised profound questions about the nature of life in the galaxy. If objects like 3I Atlas were part of a natural distribution system, then life might not be isolated to individual star systems. Instead, it could be part of a galaxy-wide phenomenon, with biological information and chemical building blocks constantly moving between worlds. The implications were staggering. If this was true, then life on Earth might not have originated here at all. We might be descendants of organisms that arrived on ancient comets, carrying genetic information from star systems that existed when the galaxy was young. Our DNA might contain the memory of worlds we could never visit, the chemical legacy of civilizations that died before our sun was born. But even if 3I Atlas represented a natural process rather than artificial guidance, its precise timing and trajectory suggested that the galaxy might be far more organized and purposeful than we had ever imagined. Perhaps the apparent randomness of cosmic events was just a reflection of our limited perspective, and on larger scales, the universe operated according to principles we were only beginning to glimpse. Chapter 10. The Approach to Fire. As October 2025 unfolded and 3I Atlas drew closer to its date with the Sun, the behaviour of this ancient wanderer became increasingly dramatic. The quiet brightening that had first caught astronomers' attention months earlier was now a full-scale transformation, as billions of years of preserved volatiles suddenly found themselves exposed to stellar radiation for the first time since the object's formation. The change was visible to telescopes around the world. Where once 3I Atlas had appeared as a faint, star-like point, it now blazed with the characteristic fuzzy appearance of an active comet. The teardrop-shaped coma that Hubble had first detected was now expanding rapidly, creating a glowing envelope of gas and dust that stretched across millions of kilometers of space. But this wasn't the gentle awakening that astronomers expected from a typical comet. The rate of outgassing from 3I Atlas was extraordinary for an object of its estimated size, suggesting that its nucleus contained materials far more volatile than anything found in solar system comets. It was as if the ancient ice had been under pressure for billions of years, waiting for this moment to release its stored energy in a spectacular display. Dr. Lisa Chen, monitoring the comet from the Mauna Kea Observatory, described watching 3I Atlas as like witnessing the resurrection of something that had been dead for cosmic ages. Each night brought new surprises as different regions of the nucleus began to outgas, creating jets and streamers of material that painted complex patterns against the background stars. The spectroscopic data flowing from telescopes around the world revealed that 3I Atlas was releasing materials in a specific sequence, as if different layers of its nucleus were being excavated by the sun's increasing heat. First came the water vapor and carbon dioxide, then more exotic compounds like carbonyl sulfide and methanol, and finally traces of complex organic molecules that had been preserved in the deepest ice for billions of years. Each new compound detected was like reading another page in the chemical history of the early galaxy. The organic molecules, in particular, were of intense interest to astrobiologists. These weren't the simple carbon compounds found in most comets, but complex chains and rings of atoms that could serve as the building blocks for biological processes. The presence of these organics raised tantalizing questions about what 3I Atlas might have encountered during its billions of years of wandering. Had it passed through molecular clouds rich in organic chemistry? Had it interacted with other objects carrying biological materials? Or had these compounds been present since its formation, preserved like messages in a bottle from the early galaxy? As the comet approached its closest point to the Sun, scheduled for October 30th, the rate of change accelerated. Material was now streaming away from the nucleus at thousands of kilometers per hour, creating the spectacular tail that would make 3I Atlas visible to amateur astronomers for the first time. But for professional observers, this increased activity came with a frustrating limitation. The timing of the comet's perihelion passage meant that Earth would be on the opposite side of the Sun during the most critical period of observation. Just when 3I Atlas would be at its most active and potentially most revealing, solar conjunction would make ground-based observations impossible for several weeks. This cosmic irony forced astronomers to rely more heavily on space-based instruments and the sparse network of spacecraft scattered throughout the solar system. The European Space Agency's Mars-orbiting missions would provide crucial data during the period when Earth-based telescopes were blind, offering a different perspective on the comet's behavior as it reached its closest approach to the Sun. But even as the observational window narrowed, the scientific community remained optimistic about what they might discover. The James Webb Space Telescope would continue to observe 3I Atlas from its position at the L2 Lagrange point, where the Sun's interference would be minimal. The data collected during these crucial weeks might finally answer some of the fundamental questions about this mysterious visitor. Would the increased solar heating reveal new layers of the comet's composition? Would the enhanced outgassing rates provide clues about its internal structure? And most importantly, would the chemical signature of materials released from its deepest layers finally reveal the true nature of the star system where 3I Atlas had formed so many billions of years ago? As we continue to follow this ancient wanderer on its journey toward the heart of our solar system, we find ourselves witnesses to an event that connects us directly to the deep history of the galaxy. Every photon of light reflecting from 3I Atlas's coma carries information about processes that occurred when the universe was fundamentally different from what we see today. The story of 3I Atlas is approaching its climax, but the questions it has raised about our place in the galaxy, the nature of interstellar travel, and the possibility of life spreading between the stars will continue to resonate long after this ancient visitor has departed our cosmic neighborhood forever. In our final exploration of this mystery, we'll discover what happens when an object older than our solar system finally meets the fire of our Sun, and what secrets that encounter might reveal about the hidden connections that bind our galaxy together. Chapter 11: The Moment of Truth. As the final weeks of October approached, something extraordinary began to unfold in the space between Mars and the asteroid belt. 3I Atlas, this ancient messenger from the depths of time, was approaching its moment of closest contact with our Sun, and what astronomers witnessed challenged everything they thought they understood about the behavior of interstellar visitors. The transformation was nothing short of spectacular. Where once there had been a faint, distant speck of light, there now blazed a cosmic beacon visible to telescopes across the electromagnetic spectrum. The comet's nucleus, perhaps no larger than a small mountain, was releasing material at a rate that defied conventional understanding. It was as if 3I Atlas had been holding its breath for billions of years and was finally exhaling in one magnificent, sustained release. Dr. Amanda Foster, leading the observation campaign from the European Southern Observatory, found herself checking and rechecking her instruments. The reading seemed impossible. A comet of 3I Atlas's estimated size should not have been capable of sustaining such intense activity. Yet there it was, streaming material into space at rates typically associated with objects many times larger. The spectroscopic data revealed layer after layer of chemical complexity as the Sun's heat penetrated deeper into the comet's nucleus. First came the expected water vapor and carbon dioxide, then increasingly exotic compounds that told the story of a formation environment unlike anything in our solar system. Methanol, ammonia, hydrogen sulfide, and traces of organic molecules so complex that their identification required consultation with specialists in prebiotic chemistry. But perhaps most remarkable was what happened as 3E Atlas reached its closest approach to the Sun on October 30th, 2025. Just as Earth's position made ground-based observations impossible, the comet underwent what could only be described as a controlled explosion of activity. The European Space Agency's Mars-orbiting spacecraft, positioned with a clear view of the event, recorded something unprecedented. The comet's brightness increased by more than a factor of 10 in a matter of hours. Material erupted from multiple points on its nucleus, creating a complex pattern of jets and streams that painted intricate geometries against the darkness of space. It wasn't the chaotic breakup that astronomers might have expected from such intense heating. Instead, it appeared almost orchestrated, as if different regions of the nucleus were activating in a predetermined sequence. The radio telescopes monitoring 3I Atlas detected something equally puzzling during this period of peak activity. While the natural radio emissions from the comet increased dramatically, as expected from the enhanced outgassing, there were also brief, structured bursts that didn't match any known natural phenomenon. They weren't the narrowband signals that would indicate artificial origin, but they were organized in ways that suggested some kind of internal structure or process that astronomy had never encountered before. Chapter 12. The Chemistry of Ancient Stars. As the data from 3I Atlas's perihelion passage began to flow back to Earth, researchers found themselves confronting evidence that would reshape their understanding of galactic chemical evolution. The isotope ratios in the materials released by the comet during its closest approach to the Sun told a story of nucleosynthesis in stars that had died when the galaxy was less than half its current age. The oxygen isotopes in particular showed signatures that were completely unlike anything found in our solar system. The ratio of oxygen-16 to oxygen-18 suggested that 3I Atlas had formed in a region where the products of massive stellar explosions had not yet been thoroughly mixed with the interstellar medium. It was like finding a fossil not just of ancient life, but of ancient stellar processes that no longer existed in the modern galaxy. Dr. Robert Kim, a specialist in stellar nucleosynthesis at the Max Planck Institute, spent sleepless nights analyzing the data. The chemical fingerprints were telling him that 3I Atlas contained materials from multiple generations of stars, each with its own unique signature of element production. It was as if the comet had been assembled from the debris of an entire stellar nursery, collecting the ashes of different types of stars as they lived and died in its birth system. The carbon isotopes were equally revealing. The ratio of carbon-12 to carbon-13 was unlike anything seen in solar system objects, suggesting formation around stars with very different fusion processes than our Sun. Some of the carbon appeared to have been produced in the helium-burning shells of massive stars, while other portions showed the signature of asymptotic giant branch stars that had enriched the interstellar medium with heavy elements through stellar winds. And so, as 3I Atlas continues its ancient journey back into the cosmic dark, carrying with it the secrets of stars that died before our world was born, we find ourselves changed by this encounter. We have touched, however briefly, something that connects us to the deepest history of our galaxy, a wanderer that has seen the universe transform from youth to maturity. Perhaps the most profound lesson of 3I Atlas isn't what it tells us about the cosmos, but what it reveals about ourselves. We are not isolated observers in an empty universe, but participants in a story that spans billions of years. The very atoms in our bodies, the calcium in our bones, the iron in our blood, were once forged in the nuclear furnaces of stars that may have been neighbours to the system that gave birth to our mysterious visitor. As you drift towards sleep tonight, wherever you are in this vast cosmos, remember that you are made of stardust, connected to ancient wanderers like 3I Atlas through the invisible threads of cosmic chemistry. The universe is not empty space punctuated by isolated worlds, but a living, breathing web of matter and energy, memory and time, forever exchanging the building blocks of existence across the infinite dark. And if you found peace in this gentle exploration of cosmic mysteries, perhaps you're ready for another journey through the hidden depths of reality. Next time, we'll explore an even more fundamental question that has puzzled philosophers and scientists for millennia: the void between atoms. What if everything you touch is actually empty space? Documentary for sleep. Until then, sleep well and dream of ancient starlight.